So in our morning session, we have seen basic character driver. So we'll continue from there. So this was the character driver. So first step is to allocate a device number. Then we have to create a file operations. You and initialize it with your cdev, and then add it in your the kernel space. So this was the driver which we have written. Then the user space app. We can also have a simple user space app. How can I write a user space app? So I have to get the device file name. So I have to open the device file. Depending on whether you want to do a read or write. I open the device file, and then I can write on a file descriptor. I can read on a file descriptor. I close the file descriptor. So perform make. So I run this in background. So my device got registered, and I have taken my caddy. So I have to replace this in the code. I have to give the permissions. So you can see when I call open on the device file node from my user application, it calls device underscore open. So is the voice audible for the others? Am I audible for others?
Yes.
Okay, so like Manish, I think you can check your connection once again. So I call write, and my write function gets called. I call read, the read function gets called, and the return value from the device was 5, device value. Return value we return 0 from the read in the device underscore read, and we get the read. And finally, when I call close, it calls device underscore read. This is the same code. Nothing is changed. I have my cadence here, and the code is same. I allocate a device number dynamically. I add it to the kernel, which is here, and I don't change anything in the open, read, write, and release. So the question is, how many times the open and release will be called in case of fork? And in case of fork, a new process is created. So how many times open and release will be called? So this is a user space code. I open the device in read write mode, and close the device. So this is for one time. Just a second. I have this code. So this is the code where we do fork. Before doing fork, I open the device. So it should call my open, device underscore open, and then I call fork. In this, after fork, a new child process is created. Will this call open? Will the open of my device driver gets called here or not? Is the question. And when I call close, we have two processes calling close. How many times the close of my device release function of my device driver gets called? Running the code. So this is the first open before fork. It called my open. Now you can see current. There was no one more time open call, even if a new process, child process is created using fork. So in, and both of them has called write, and both of them were closing the file. Even though both of them were closing the file, you can see the release called only once. So you can observe here open got called only once and release got called only once. So open and release function is only called once, which we have seen. So when you do fork, what happens is it will not create a new file structure. So it will not create a new file structure. It will only copy the file structure. So open will not be called. And when you call close, close function will call the release method only when the counter of the file structure becomes zero. So there is a counter in the file structure. Only when the counter of the file structure becomes zero, the release will be called. This is the reason why only release code was called once. So till here the counter, when you call closing file, the counter was not zero, so the release was not called. In the second close call, the counter became zero and the release got called. So if you want to go, like if you want to find out to print the value of counter, you can go into the Linux source code. So we have a struct file. There is a field known as count. If you can print this count value, you can see the value of count. Only when the value of count becomes zero, your close will release will be called. So I have this old code that I only open the device and I close the device. There is one more code there. I do the same. This is the copy paste of the. I open the device node. I close the device node. I compile it. So I'm first starting the user space at first one. So it has called open. In the second terminal, I'm starting the user app 2. So it should have also called open. So open got called. Now when I stop this, you can see release got called. Again, I'm calling close in the second app, release got called. So you can see the behavior here. The behavior is not the same in case of fork. Right? In case of fork, when you create a new process using fork, the open and close is only being called once. But if you're running it separately, when there is no parent-child relationship, each open call will be related to each device driver open, and each close will come to device release. As the process is different, so a new file structure will be created. Hence, you will be having open to open and close to release. So the first, we'll be looking into the structures which are present here. First structure is struct file, which we have seen just now, which is this structure, struct file. which is defined in Linux infs.h. This structure is different when compared to the capital file of user space program. So in user space program, you have like capital file. So this is different when compared to the user space programs capital file. A file is defined in the C library and it will never appear in the kernel. Whereas a struct file is a kernel structure. It will never appear in the user program. So this file structure represents an open file. This is an important point. It represents an open file. So whenever you open a file, a new file structure is created by the kernel. So every open file in the system has an associated struct file in kernel space. So when you call open from your user space code, kernel will create a struct file in kernel space. So this is created by kernel on open and is passed to any function which operates on the file. Like you can see the structure is being used almost everywhere. It is present in the open, it is present in the release, it is present in the read, it is present in the write. So this file is used almost in all the file operations. So, and it is closed when all the instances of the file are closed. Kernel will release the data structure. So an open file, this is important, an open file is different from a disk file. So when you create a file by saying touch, this is a file on the disk. This is different than open file. So disk file is represented by struct inode, which we'll be looking at it. Open file is represented by struct file. So when you open a file, a new structure is created by the kernel, struct file. But when you create a file using touch command or any other thing, it is represented by struct inode. So these are the important fields of struct file. First, field mode, whether you open the file in readable or writable. What is the current position in the file? Offset. So again, flags like read-only flag, non-blocking sync. What are the file operations associated with the file? So this you have here. File operations which we have used with cdef. And you can also have something known as private data. So you can have a void pointer. So this open system call sets this pointer to null. This is a system call implementation, which will set the pointer to null before calling the driver open call. And the driver can use this for its own purpose. So it is useful for preserving state information across system calls. We'll be looking into examples of using private data, and this is used for preserving state information across system calls. So I have updated my open the method of the driver. So you can see I'm using the f underscore flags to find out whether I have opened the file in read-only mode, write-only mode, or read-write mode. I'm also checking whether it is into different like flags are passed here. And also I'm printing the file police of using fpost. So this is the fields which are present in file, struct file. From the user app, I'm opening the device in read-write mode, and then I'm closing the device. So I'm checking whether this is being printed in the kernel space. Then I'm opening the device in the read-only mode, opening the device in write-only mode. I'm also passing additional flags like non-blocking, etc. to check whether my driver is printing correctly or not. So first I have opened the file in read-write mode, and you can see the device driver has printed read and write mode. Then I have opened in read-only mode and has printed the read-only mode. And write-only mode have passed O non-blocking, so it has printed I've also passed append. That's going to. So this is the struct file which we have seen. So each open file you call from user space, kernel creates a struct file in the kernel space. And it has the file operating mode, file offset, private data, file operations, etc. And it also, you can see from this code, it also has a pointer to the inode. It also has a pointer to the inode. We'll be looking into an example there. So we have seen struct file. Then there is a next structure is struct inode. So how many of you know what is an inode? What is an inode?
It is a structure for a file.
It's a structure of a file. We just seen a struct file, right?
Mm-hmm.
We have just seen struct file. Is it not the structure of a file?
No. When some file is created, that structure is created for that file. That is inode.
Okay, perfect. So inode is the structure which tells the information about the file. So like what is the file permission? What is the file permissions? What are the file timestamps and all? So when you create a file, it is actually creating an inode. So each and every file has an inode number. So you can verify that using stat command. It will give you all those like size is stored in the inode, how many blocks, what is the block size, type of the file, user ID, inode number. So this all information is stored in a structure known as inode. So this is what is struct inode. Struct inode is used to identify a file in the file system. So it represents a file on the disk. So it is different from struct file. Struct inode is different from struct file. Struct file is whenever you open a file, struct file is created. But whenever you create a file, struct inode is created. Some of the important fields are mode, who created this file, user ID and group ID, inode number. It also has device number. So device number is present in struct inode. Device number is not present in struct file. It is present in inode. It has struct CDEV, pointer to a CDEV structure. So kernel developers has added two macros using which you can obtain the major and minor number from an inode. I minor is will give you the minor number from the inode. I major will give you the major number from the inode. So if I have a dev underscore t, how can I find out the major and minor? From dev underscore t, if I want to find out the major and minor number, what are the macros for it?
We use major and minor macros.
Yeah, perfect. The major and minor macros if you have a dev underscore t. If you have inode, you can directly use I minor and I major to find out the major and minor number.
So I have one question. Can you open the file? Yeah. So the file on the file system is represented with struct inode. So
Yeah.
usually all the files are block devices, right? So why we have a char device inside the struct inode?
All the files are block devices. So
Yeah, yeah, yes.
this is a file system, right? Block device is a memory device, right?
Okay,
This is a file system.
okay.
File
So
system is stored
files.
on a block device.
Okay, okay.
So in the open, I have updated the code. So I'm here printing the mode, permissions, the user ID of the device, group ID, inode number, I major and I minor. To get the major and minor, and I can also use major and minor to get the major and minor number. So you can see it's a macro in the can see I major is just doing what we are doing here. Major of inode and RDEX. So I can also access the inode number, inode structure from file. We have seen file has a f underscore inode pointer. So this also prints the inode number. This is the code which just opens a device, calls write, opens the device, calls write, calls read, closes the device. You can see it has printed the permissions 066. We have given 666 to dev my device. So it has given the permissions of the file 666, and the C is what? This 2. And then we have user ID and group ID. And you can see the user ID and group ID are for root. And ID root, you can see the user ID is 0, group ID is 0. And inode number is 489, major minor number are 240. So I can also find out using stat. So stat dev my device. My inode number is 489. This is what is the inode number here. So this is the struct inode. We have seen the differences between struct file and struct inode. Struct file also has a pointer to struct inode. Struct file is representing an open file. Struct inode represents a file on the disk. So we have seen struct inode. Let's see an example. We'll understand struct inode versus struct file. It's a very simple example. I'm printing the address of the file number, file, struct file, and inode. I'm just printing the address of the variable inode and file. So in the code, I'm opening the device, and this is the same code. Opening the device, performing write, then read, and then close. So you can see the struct file address and inode address. What will happen if I call the user app again? Will those which value will change? If I call user app again, will the both pointers will be different, or anyone will be same, or both will be same? So just remember, struct file is represents an open file. Struct inode represents a disk file on the disk.
File could be different, inode could be same.
Yeah, perfect. As we have closed the file, kernel has removed the struct file pointer. So deallocated the struct file pointer. Now again we are opening a file, so a new file struct will be created. But the file already exists. So this file already exists. So this will be same. So you can see this has changed. As a new struct file has been created by the kernel, but inode is the same because it's a disk space. Now if I delete my device, okay, and I create it again, mknode /def my device, C, it's a C and 240, 0. So what are the yes, name type is an element. So no enough common here. So I have now created my device again. So let me give permissions again. So if I run the user app, will I get a different inode structure or a same inode structure?
Think different.
So we'll get a different inode structure because that file has been deleted from the disk and a new file has been created. So we'll be getting a different inode structure. Also, you can see inode number should have is same here for now. So this is what about struct file and struct inode which are used in our device drivers. So the next fields we'll be looking into read and write. So you have here count. So this count represents how many bytes you want to read. And then you have offset. Same thing here, how many bytes you want to write is count. This is the write count, this is the read count. And then you have offset. And I have a user buffer. So whatever user is passing is coming to the user buffer here. Then I have the struct file, which represents the open file. So what I'm doing is I'm trying to print whatever user is passing. So I'm trying to print the user buffer. Okay. So I'm trying to print the user buffer. In the user space app, I'm just calling write and read. So will this work? Can I directly print the user space code from my kernel driver? Can I directly access the user space buffer in the kernel driver? The kernel driver is running in kernel mode. User space application is running in user mode. So can a kernel driver running in kernel mode access the user space code process address space? So let's find out. Let's find out. What I will do is I will do a cross compile. I will not run it here. So what I have done is I have just made a command alias for this cross compile. So when I do a cross compile, it will do a make cross compile, and it will also cross compile my user app. So I do a cross compile. So, cross there's some problem with the script. Okay, let's do a cross compile from here. Start going there. So, yeah. So I have cross compiled this. It's for cross compile for ARM. Then I also need to cross compile the user app. So I have cross compiled the user app for ARM. Now let me start my demo. So demo, let me start my demo now. So this is I'm doing because I don't want to freeze my system. So it's starting my demo there. I have my user app. It's 4964. 4964. This is the same hello.q is present here. I have my user app. So let's load the module in the Emu. So it has loaded the module and I have received 253 as a major number. And it should have created my device. So it already is running in root, so let's not change the permissions. Now let's try to run the user app. So it has called open and my device open is called. And now you can see when I call write, it failed. Says page fault. So when I call a write, you can see it has given me an oops message saying page fault. The module was hello. So you cannot directly access. This means you cannot directly access the user space pointer in the kernel space. You cannot directly access the user space address space in the kernel space. So is this clear? Actually, I've cross compiled it so that avoid of restarting my machine. I've cross compiled on for Chemo arm and then I've used Chemo to run that code. So you cannot, what we have seen is you cannot directly access the user space memory in the kernel space. So how to access the, so how can I access the kernels in the kernel space, the user space data? So there are macros which are provided and their functions which are provided to access the user space data in the kernel space. So this header file has been changed. So okay, we have not seen. So why we cannot access? So direct access page of a user space pointer can lead to the incorrect behavior because we have seen the page fault. That particular page may not be mapped in the kernel space. So it can lead to an incorrect behavior. Kernel loops can happen, which you have seen. Security issues. Because of these reasons, you cannot directly access a user space pointer. So they have provided macros and functions to access the user space data. The header file is changed. If you're using an old header file, this is asmuaccess.h. Old Linux versions like before 4 point something. The latest Linux version needs Linux uaccess.h. We have changed the header file address. So if you're using the latest like 5 point, which I'm using, you have to use Linux uaccess.h. So we have 4 functions here: put user, get user, copy to user, and copy from user. All of these functions return 0 in case of success and some other value in case of error. So put user is used to put a value in the user space. So if a user is calling read, we'll be using put user. And then we have the reverse get user. Then we have copy to user, which will copy from the user space to kernel space. No, from the kernel space to the user space. These are little confusing. Copy to user is to copy from kernel space to user space. Copy from user is copying from user space to kernel space. So let's see an example that will be clear for you. So copy from user, it has 3 parameters. First one is 2. This is the kernel space pointer. You can see this is the user space pointer. This is the added hyphen user. And then how many bytes to copy. In the header file, as I said, depending on your version, you have to use this. It copies a block of data from user space into kernel buffer. So first one is the destination buffer. This is the destination buffer. In source buffer and length. On success, it gives 0. On failure, it gives a non-zero value. Like if it is unable to copy some bytes, it gives non-zero. So I have implemented the write function. I have a kernel buffer of 100 bytes. I have initialized it to 0. I'm printing the addresses of kernel buffer and user buffer. So you can see I'm not accessing the buffer. I'm just printing the address of the user buffer. So this should be fine. Then I'm calling copy from user, copying user buffer into kernel buffer, count bytes. And I'm printing the return value of copy from user. Copy from user returns 0 on success. On failure, it will return how many number of bytes it failed to copy. And then I'm printing the kernel buffer. And I'm just printing the count and offset. And finally, I'm returning how many count, whatever the count the user has. I'm loading my module. The module is loaded. Giving the permissions. So let's see what code which we have. So this is the old code which actually failed in the previous code. Open the device, call write hello, and call read, and just close the device. So I'm opening the device, and you can see this is in the kernel space. Hello got printed in the kernel space. We have transferred hello from the user space to the kernel space, and copy from user has written 0, and 5 is the number of bytes which we have written from the user space. And in case of read, we are not implemented read, so we'll just skip further. So this is how we can access kernel user space buffer in kernel space. We have to call copy from user to copy the data into the kernel space. I have one more user space code. So what I'm doing is I have a pointer, character pointer null. I'm just passing that null here. I have not allocated any memory here. I'm just passing that null here in case of write. So what will happen now? Will the kernel crash? Driver crash? No. If I run this code, or will the copy from user will be handling this all these things? Let's see. So I have called open, and you can see copy from user has returned 5. You can see user buffer is null here. And copy from user has returned 5. This means it is a non-zero value, and this value represents number of bytes which have not been copied into the kernel copy from user code. The 5 which we have passed in write is being returned by the copy from user. So you can see this is being handled by the copy from user. If we don't have this copy from user, and if somehow a user passes null, then it should crash the system. So this is the reason why we should use copy from user. So we have seen example of copy from user. Let's see an example for copy to user. So copy to user, again, it copies from the kernel into the user space. This is the reverse operation of copy from user. And you can see user pointer is here. And it also returns 0 on success, non-zero to indicate number of bytes which are not transferred. So I have updated this read code. I have a kernel buffer which has content kernel, and I call copy to user. This is the user buffer, and this is the kernel buffer. I'm copying from kernel buffer to the user buffer. That's it. In the user's code, I open the device, I call write, and then I call read. So when I call read, I should receive the kernel which it has written there. So let's see whether we get open, right? We have written hello, and you can see the buffer from the kernel space. I have received kernel from the user, from the kernel space into user space. Of course. So we have seen how to copy the data from user space to kernel space using copy from user and copy to user. And then let's look into put user and get user. So before going there, let's find out what is a Jiffy. So Jiffy, according to Wikipedia, it is a term used for unspecified short period of time. So any unspecified short period of time is known as Jiffy. But in Linux kernel, Jiffy is a global variable. It stores a number of clock ticks since you have boot. This is present in this header file. So this is a global variable. So you can access it from any kernel code. Jiffy is a global variable. It will store the number of clock ticks since boot. So let's write a character driver, which when I read, it returns the value of Jiffys. So on the read call, I'm returning calling put user. Put user will put the value of Jiffys into the user buffer. So if you are transferring like integer, character, short, and all, you can use put user. If you're transferring more than this, then you have to use copy from user. So put user is putting the value of Jiffys, which is a 64-bit value. So you have to typecast it. You have to typecast your character user buffer to 64 and putting it in the user buffer. This is not really used. In the test app, I'm opening the device Jiffys. I'm reading the first value. I'm storing it in old Jiffys. I'm printing this value. And then I'm going for sleep for 1 second to find out like how many ticks are happening after 1 second. Jiffys will be incremented of like for 1 second. Then I'm reading this new Jiffys value. And then I'm printing the difference between the Jiffys. So let's do a build. So I have registered this and it's my device. So I have my Jiffys here. So this my device was of the old, which we have used MK node. So I have my Jiffys. Now I can run my test app. So it first printed the first read and then the second read, and it gave a difference of 250. So this means for 1 second, we got a difference of 1 second. So this means Jiffy value increments by 250 every second. So every second 250. This means timer is configured to generate 250 interrupts per second. So timer, you can also run it again. You can see we get a different value here. We have 596, we have 920. I can see the difference is 250. So this means the timer is configured here to generate 250 interrupts every second, and each timer interrupt will increment the value of G. And we have used put user, and basically they say put user is faster than copy to user because maximum it has to copy like 8 bytes. Normally it is like almost same. There may be some differences. So put user, if you know, like if you are copying normal integer character and all, then you can use put user and get user. So next one is get user. Put user is to write to the user space. Get user is to get the data from the user space to the kernel space. So like for char int. But if you're using a structure, you cannot use put user or get user. You have to use copy from user and copy to user. So I have a device named my int. So in the write call, I'm getting it from the user buffer. I'm storing it in a value. The value is a global variable here. So in the write call, user writes and I store it in the value. When user reads, I call put user and give the value of this to the user buffer. And you see, typecasting it to int. So you have to typecast it to the proper type, otherwise you get different values. So previously it was 64-bit, so we have typecasted it to U64. And from the user space app, I'm opening the device file, my int. I'm writing 10 here. I'm just changing the value to 2. And then I'm calling read on the value. So I should get the latest value, whichever I have written on this. I should get 10 here. This I'm updating to see I get the updated value or not. And then I'm closing the file. So open. I call write, device write. I call read. I got 10, which I have written when I have called write. Press close. I think we should stop it from here. And we can continue in our next session. The copy users. Try to answer these questions.
What? Struct 5. I know.
Struct I know.
I minor.
Small I know.
Yeah. No. All. With user.
Perfect.